Now in case of estimating beta, we got something which was both unbiased and best in some sense, blue. Can we make such a statement about the sigma square hat? Is it best in some sense? Does this have the smallest possible variance? Well, we really cannot talk about that because you notice it is already a quadratic expression in y. So if you want to talk about its variance, we will run into fourth moments of y, and our Gauss-Markov setup has assumptions only up to the second order moment, from which you cannot make any guess about the fourth order moment. They may not even exist. As a result, just based on the Gauss-Markov assumptions, we cannot make any optimality claim for this sigma square hat, other than the fact that it is very natural. We are looking at the norm square of the error, and sigma square basically controls the amount of error, so we have taken norm square of that and divided by a suitable factor, so that should be a natural thing. However, if you put some further assumptions, then it is possible to show optimality, and that is not very difficult. If I assume further that the distribution of epsilon is also Gaussian, so we already have mean zero variance sigma squared I. Now I also put the assumption that it is Gaussian, which completely specifies the distribution. You have moments of all order, etc., etc. In that case, you can have a much stronger result which says the same sigma square hat will also be UMVUE, uniformly minimum variance unbiased estimator. The fact that it is an unbiased estimator is something which is already proved. We do not need the Gaussianity assumption for that. But under Gaussianity assumption, one might show we do not want to go into that. It's pretty straightforward using a result that I am sure you have or you will learn somewhere during your visitor days in parametric inference, which says that for an exponential family distribution under certain conditions, the interior of the parameter space being non-empty, the natural sufficient statistics also happens to be complete sufficient. So from that you can see that the sigma square hat expression that we have given is a function of complete sufficient statistics, and hence we know it must be UMVUE. Interestingly, under the same assumption, the Gaussianity assumption, the blue that we showed, beta hat, or the beta hat if x prime x is non-singular, or those c prime beta hat things if x prime x is possibly singular, so all the estimable parametric functions. The least square estimators that we saw, c prime beta hat, they are also UMVUE. So we are making a stronger statement. Earlier we said, look at the class of all linear unbiased estimators, they have the minimum variance among that class. Now I am extending the class. I am saying not necessarily linear unbiased, just unbiased. I will allow even non-linear estimator. Even then, this will have the least possible variance. So I am not removing the unbiasedness condition, but I am removing the linearity condition. Again the same proof, we will see that x prime y will be a sufficient statistic, the complete sufficient statistic for the beta vector or that c prime beta thing. And from that you use whatever, the Rao-Blackwellization theorem, etc., etc. I am not going to go into those things. If you have already done that in your parametric inference, you will be able to do it. If not, you will not be able to do it. So you will see that it will be UMVUE. This fact is not of any great importance in practice because often the error distribution will not be Gaussian, and even if it is Gaussian, it merely says that the common sense estimator, the least square estimator, the blue, it has already lots of good properties, it has yet another good property. But it is good to know.